Hello everyone! In this video I'll be doing a review for exam 1. I'll walk you through some of the topics that we've covered since the beginning of the semester, and I'll show you some sample questions to go along with each of those topics. Our exams for the course are digital, so I'll also be showing you what those questions might look like in a digital environment, very similar to the quiz questions you've been tackling each week. Most of our questions are some form of multiple choice. There are a couple of others, and I'll show you as we encounter them throughout the exam review. All right, let's get started. At the very beginning of the semester, we learned about print statements and escape sequences. If we want to give output to the user, we call the print format function, which is printf. It's comprised of the function name, which is printf, and then inside a set of parentheses, we have the control string and some number of arguments. In our simplest printf statements, the argument list is empty, like in this example. Everything in between these two quotation marks is the control string. And in this case, there aren't any arguments because there's no variables that we're printing out. And to go along with print statements, we learned a few escape sequences. In particular, we learned how to insert a new line into our output and how to make tabs, which insert 8 blank characters into our statements to kind of separate things out a little bit. So we can add those to this print statement, and we would see something like this. So a question that would go along with that is over here in question 1. It says, which of the following lines of C code prints out 3 tab characters and possibly a few others? It's a multiple choice question. So we're looking through our choices to figure out which one of these prints out 3 tabs. Now this first option prints out the word tab 3 times. So option 1 is just the strings tab, 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 which is not what we're looking for. The second option just prints a series of new lines, so it prints new line characters. But this third option has the /t's in it, so it's going to print a tab and then 2 t's, another tab and then 2 t's, a third tab and 2 t's. This last one kind of looks like it has a tab escape sequence, but those slashes are going the wrong direction. So this is the one that we want, the one that has the 3 tabs and these bonus T characters. After that, we learned about some basic data storage and the corresponding percent codes or conversion characters. We have 4 basic data types: int, which stores integers and uses %d, char, which stores characters and uses %c, float, which stores real numbers and uses %f, and doubles, which also stores real numbers but at a higher level of precision and uses %lf. So if I were to ask a question like, which of the following is the correct percent code for characters, then we should be able to select %c for characters. Now that we have our basic data types, we can declare variables of that type and also initialize them. A basic variable declaration just has the data type, a name, and a semicolon. So for example, if we were looking to declare an average, we could declare that with the float data type, a variable name avg, and end with the semicolon, and that would declare something of type float. We might also choose to declare a variable and initialize it at the same time, like in this example. We can make another variable called sum This one's also of type float, but we've initialized it to 0 by adding in the equal sign and its initial value. Now once a variable is declared, we don't need to precede it with its data type anymore. Once it's declared, we can go ahead and use it in assignment statements. So let's look at a sample question for variable declaration. This one says, which of the following correctly declares a double called sum with an initial value of 0? So we want to figure out which of these options has both the correct data type, the correct name of the variable, the correct initial value, and all of the correct syntax. This first one has a float as the data type, which is not what we're looking for. We want a double. So this one has the correct data type and the correct variable name, but after the equal sign, we don't have the correct syntax. This isn't a double literal, and there's no semicolon at the end. This one is, again, missing the correct data type, and so this last one is the one that we're looking for. The one that does have the correct data type, the name sum, and the initial value of 0, the semicolon at the end, all of the correct syntax is in place. Okay. Another way that we can get an initial value for a variable is with our scan format function. This allows the user to input information for us when we store that in a particular variable. Now, so far, our scanf statements have had a fairly rigid form. That control string usually just contains a single percent code, also called a conversion character, and usually just one. We only try to read in one piece of information at a time. So we're going to have the percent code, and then after that we have the ampersand and a single variable. We're only reading in one piece of information, so we're only going to have one argument, and that argument is ampersand, then variable. So this is another way that you can think of the scan format function. It has the function name scanf, the set of parentheses, the control string, remember the string is in between these two quotations, contains a single percent code, then a comma, then an ampersand, this and symbol, a variable, and at the end, the semicolon. So let's take a look at a sample question that might go along with that. It says, which of the following reads in a double into a variable of type double called radius? So we're going to be looking for the one that has the correct syntax, that has the correct percent code, and the correct variable name. Now, if we look at our options real quick, we can see that all of them start with the correct function name. They all start with scanf. So we're just going to be looking for the one that has the control string, the ampersand, and the correct variable name. So it'll be this last one here. After we have an initial value for our variables, we often change them with assignment statements. The syntax for an assignment statement is very rigid. We have a variable on the left-hand side of this assignment operator. On the right-hand side, we have some expression. Expressions can be a lot of things. It could be an arithmetic expression, it could contain a function, it could be a single literal, or some combination of those. So for an example, let's assume we have some integer x. And we can assign x a value from an expression like 6 times 4. And in that situation, x would then take on the value of 24. We would say x is assigned the result of this expression. And so this expression is fully evaluated. We figure out what 6 times 4 is and store the result back into the variable on the left-hand side of the assignment operator. And x then keeps that value. It remains 24 until some other assignment statement in the program modifies it. And if we encounter another assignment statement, x then changes its value. It's updated to, in this case, x is assigned the value 9. And from that point forward, it has 9 instead of 24. So this question asks about the correct syntax for an assignment statement. It says, what should the following statement be changed to in order for it to be syntactically correct? So it kind of tells you ahead of time that this statement is incorrect. We're looking for the correct version. Well, this says 3 is equal to x, which doesn't follow the syntax for an assignment statement. The variable that we're modifying has to be on the left. In this case, it's on the right, so that's the problem. So we want to examine our options and find the one that has the variable on the left-hand side and the expression that we're trying to update it to on the right-hand side. In this case, the expression is a single literal. In our other options, this one has 2 equal signs, which means it's a relational operator, not an assignment statement. This one's also a relational operator. And this last one contains the relational operator and the variable in the expression are in the wrong order for an assignment statement. So in order for this assignment statement to be syntactically correct, we have to put x on the left-hand side and its new value on the right-hand side, and use a single equal sign as our assignment operator. Now, some values in our program do not vary. They're not variables. So instead, we like to declare them as constants. Well, similarly, the constant definition also has a very rigid syntax. It starts with this preprocessor directive for define, the pound symbol followed by the keyword define. And then there's a instance of white space, then a name, some more white space, and then the value. So if we want to declare something to be constant in our program, we use that pound symbol in the word define. And one that we used in a couple of different places is 1/2. So we would do pound symbol, define, space, the name, which in this case is half, another space, and then the value. In this example, it would be 0.5. And then we would be able to use half in any of our arithmetic expressions where we need to divide something by 2. And one of the interesting things about that is that we're declaring it as 0.5 instead of 1/2 because C has some really special rules about integer division. Now in C, it distinguishes between integer division and real division and supports both. In integer division, we always get an integer result. Anytime we take an integer and divide it by another integer, we do integer division and get an integer result. So as an example, let's say we have x equal to 17 divided by 5. This example uses what we call integer literals. 17 is an integer, and 5 is an integer. So x would actually take on the value 3, because that's how many times 5 goes into 17. And since this is doing integer division, we only get the whole number result, none of the parts of a number that would normally follow this type of division. It's integer division, 17 is an integer, 5 is an integer, so 17 divided by 5 is going to give us an integer. So integer division is something to keep an eye out for in our arithmetic questions, like in this example. It says, what is the value of the following arithmetic expression? Where we have 4 times 9 plus 27 divided by 2. This is a great arithmetic question because it's a little bit integer division and it's also a little bit order of operations. So we need to keep in mind that multiplication and division have a higher precedence than addition. So we're going to do 4 times 9 and 27 divided by 2 first. And in addition to that, we'll be looking out for this integer division over here. So first we'll do 4 times 9, which is 36. And then we're going to do 27 divided by 2. So 27 is an integer. 2 is an integer. So we're going to do integer division and ask how many times does 2 go into 27? And that is 13. So we'll add those two values together to get a final answer of 49. And in our sample question, we should select 49 to match. Now, if we were doing real division, we would actually get 13 and a half out of this. So it's really important that we recognize that both of these are integers and prompt us to do integer division. If we wanted to do real division, there's a couple of different solutions. If we're working with literals like these guys, we can make one of them not an integer really easily by adding 0.0. But if we're working with variables, we're going to instead use what's called a cast, where we temporarily treat one of our values as a different data type. One cool thing about integer division is it also gives us the modulus. And the mod operator produces the remainder when one integer is divided by another. So as an example, if we were doing something like 16 mod 3, we would be looking for what's the remainder when the integer 16 is divided by integer 3. Now 3 goes into 16 5 times, and 5 times 3 is 15, and 16 minus 15 is 1, so we would get something like this. 16 divided by 3 is 5, remainder 1. And if we are doing the mod operator, we're going to see this remainder portion. And you'll see that our example question is very similar. What is the value of 29 mod 9? So what's the remainder if we take 29 and divide it by 9 using integer division? 9 goes into 29 3 times, and 3 times 9 is 27, which means there's 2 left over between 27 and 29. In the same chapter, we talked a little bit about the math library. Math library contains a lot of functions, but we talked about 3 in particular. First is the power function, which is called pow, and takes in 2 double values and gives us back the result of x raised y. The absolute value function, which gives us the distance from 0. So the absolute value function, if we give it a positive number, we're going to get that same number back. But if we give it a negative number, we'll get the positive equivalent because that's the distance it is from 0. One interesting thing about absolute value is that it only works on integers. If you want it to work on real numbers like floats or doubles, you need a different function from the same library. Our third function is square root, which of course gives us the square root of a positive number. This one can be a double. So a question that we could ask about the math library, something like what function finds the distance of an integer from 0? And that is our absolute value function. While we were learning about pre-existing functions, we also took a look at the pseudo-random number generator, which is part of the standard library, stdlib, and allows us to get a pseudo-random number. Of course, there's not any true random numbers in this library, but we can approximate using a random function that is called rand. And we saw some examples where rand doesn't necessarily work well by itself. So we have to seed the pseudo-random number generator with this seed function srand. And typically we use something from the time library to make sure that our seed is a value that is continually updating. We typically use the time function. So in order to make this work, we need to seed the number generator. We only have to do this once, but we'll call the seed rand function on time. And that'll give us access to a pseudo-random number that we can then generate by calling the rand function. Now the number we get from rand is in a range between 0 and 32,767, which is quite large for most of our purposes. So we learned how to modify that using the mod operator. When we mod by a number, we're guaranteed to get a value between 0 and 1 less than the number we're modding by. So in this case, if we mod by 100, we're going to get a value between 0 and 99. So a question that makes use of both the random number generator and the modulus asks which of the following expressions evaluates to a random integer in between 1 and 50. You may assume that the random number generator is already seeded, so we don't have to worry about that. We just have to determine which of these expressions evaluates to the range that we're looking for. So this first one, if we mod by 50, we're going to get values between 0 and 49. So we're not looking for that one. But if we add 1 to that range, if we have 0 to 49 and we add 1, then we'll have from 1 to 50, which is what we're looking for. The next one will give us from 1 to 49, and this one will give us from 0 to 48. So if we want from 1 to 50, we want to pick this one right here. Next, we moved on to our conditional statements chapter, which contains conditional expressions and if statements. While loops and for loops also depend on these conditional expressions, so they're very important to us. Conditional expressions relate to individual expressions with a relational operator. And there are 6 relational operators that we should know about. There's equal to, not equal, greater than, less than, greater than or equal to, and less than or equal to. And these conditional expressions evaluate to true or false, where both of these are represented by an integer. So true is represented by 1, and false is represented by 0. So this question about relational operators says which of the following is not a valid operator. So this one is not equal to. This one is less than or equal to. This one is greater than. So all of those are valid. This one is not a relational operator. This is an assignment operator. A single equal sign is an assignment operator. It's part of an assignment statement. It takes 2 equal signs to make the relational operator equal to. The first thing that we used conditional expressions in is if statements. These are a reminder of the general syntax. We have if as a keyword. Inside a set of parentheses, we have a conditional expression. And if that conditional expression evaluates to true, we run everything in between these 2 brackets. If it's not true, we might have an else statement where instead we'll run everything between these two brackets. So a question that involves if statements might look something like this. This is commonly referred to as a tracing question, where we are given a segment of code and we're asked to read through it to figure out what it's doing. We trace through it. It says, what is the output of the following segment of code? Well, output is produced by printf statements. So we're asking, read through this segment of code and tell me what's going to be printed by any of those print statements. We have two integers, a and b. A is 7 and b is 11. And the first thing we say is if a is greater than 7, print a. Well, a is not greater than 7 because this is strictly greater than, and 7 is not greater than 7. So we're not going to print a. And we'll check our next one. It says if b is greater than a, print b. Since b is 11, that is greater than a, so we will print b. And that's all we're going to print because this else statement says we only print c when b is not greater than a. When we have a lot of conditions to consider, we typically do something called implicit nesting. You might also hear this called an if-else-if statement, where if this first condition is not met, we can go on and check a second one using else if. If this condition is not met, we can go on to the next one. If any of these conditions are true, we will run the statements in between their brackets, and that'll be the only one that we run. So if this one is true, if this first conditional expression is true, we'll run all the statements in between these two brackets, and then we will skip everything else. So our sample question for implicit nesting is our first look at a coding question, where I would ask you to write some portion of code. It says, consider a program that determines if an input year is a leap year or not. Most years that are evenly divisible by 4 are leap years, but there's an exception. Years that are evenly divisible by 100 are not leap years, unless they are also evenly divisible by 400, in which case they are leap years. Now I would ask you to type the statements or constructs you would use in each of the marked sections to complete the program. Now, several of the normal things that belong in a program are already present. For example, we have our preprocessor directive to include the standard input and output library. We have the start of the main function, the year is declared, and we go ahead and have the user enter it. So this particular question is really just looking for your knowledge of if statements and your ability to nest them either explicitly or implicitly. And it says here, this is where you want to complete the main function. So this is what we are trying to type up. The answer to this question should be inserted where this comment is, and the program should then run correctly. And we're going to type our response in this box down here. So since we already have the year, all we need to do is process whether or not it's a leap year. And all of our criteria comes from the problem statement. If it's divisible by 4, it might be a leap year, unless it's divisible by 100, in which case it's not, unless it's also divisible by 400, in which case it is. So we're going to check 400 first. This is our most guaranteed to be a leap year. So if the year is evenly divisible by 400, then this is a leap year, and we want to indicate so. We know it's evenly divisible if we take the modulus and we get a remainder of 0. It means 400 evenly divided into year. So if that's the case, then this is a leap year. If that's not true, we'll check if it was divisible by 100, which the problem statement has said is not a leap year. If we've checked both of these conditions and neither are true, we're allowed to refer to the definition that we're probably most familiar with, which is that if you can divide it by 4, then it is a leap year. And if none of those are true, then this must not be a leap year. Then we can have this final else statement catch everything else. Everything that's not divisible by 400, 100, or 4 is not a leap year. Now, tab, like you would normally use in your IDE, will not work on the digital environment for the exam, but you can control your indentations with these 2 buttons up here, so you can increase or decrease indent. So if we would like to make it look nice, then we're going to increase the indentation for those portions that are inside the if statements. After conditional statements, we started looking at loops. And a lot of loops make use of these shorthand statements that I would like you to be familiar with. Even if you don't use them yourself, you should recognize them when other people use them in code. This first one is an increment by 1, where whatever variable you're using increases by exactly 1. This second one is a decrement by 1. And this last one allows you to modify a variable in kind of an interesting way. It's the same as saying variable is equal to itself, whatever that operator is, and then that expression. So you most commonly see plus equal, especially with sums, but any of our basic operators work. So you could also have minus equal, times equal, divide equal. And we use those quite frequently in our loops. The first of which is the while loop, which starts with the keyword while, and then inside a set of parentheses has a conditional expression. And as long as the conditional expression is true, we run what we call the body of the loop. Everything in between these 2 brackets will be run. So as an example, we can look at this question, which says, what is the output of the following segment of code? Very similar to the previous tracing question we were looking at. We want to read through this segment, and of course segment indicates it's not a complete program, it's just part of one, and find out what it outputs. What are the results of this print statement? What are we going to see if we were to run this and look at the output screen? So what we want to do for this type of tracing question is keep track of the value of A, the value that we're modifying within the loop, using as part of our conditional expression and printing to the screen. We want to keep track of A, which starts at 1. We want to keep track of what we're outputting to the screen. So A is presently 1. We want to know, is A less than 80? Well, since 1 is less than 80, this is true. And we'll go into the loop, run everything in between those 2 brackets. Now the first thing says that A should be replaced with A times 2 plus 3. So we'll do 1 times 2, which is 2, plus 3, which is 5, and assign that value to A. So A is now 5. And then we print the integer A. So we're going to print 5. And since that's the end of the while loop, we'll go back and check the conditional again. Well, 5 is still less than 80. So we're going to modify a by doing 5 times 2 plus 3, which is 13, and assigning that value to a. So a gets replaced with 13. And then we print a, so we're going to print 13. And check the conditional again. 13 is still less than 80. So we assign a the value 13 times 2 plus 3. 13 times 2 is 26, plus 3 is 29. So we'll replace a with 29. And then we'll print a. Now 29 is still less than 80, so we're going to run the loop again. We'll say a is assigned the value of a times 2 plus 3. So we're going to take 29, multiply it by 2, and add 3. We'll get 61. And then we're going to print 61. Now 61 is still less than 80, so we are going to run the loop a final time, and we'll do a is assigned the value of a times 2 plus 3, so we'll take 61, multiply it by 2, and add 3 to get 125. So a is assigned the value 125. And then we'll print that value. So we're going to go ahead and print 125. When we get to the end of the loop, we check it one final time. 125 is not less than 80. So that allows us to break out of the loop. Now the output produced by this loop are these numbers, 5, 13, 29, 61, and 125. So we need to find the option that matches that. After while loops, we went on to for loops, which have a different syntax. They start with an initialize statement, then a conditional expression, and then commonly an update function. So this depends a lot on what you want your loop to do. For example, a common initialize statement would be I equal to 0. I is a really common counter variable name. We would set up a conditional expression to control the number of times the loop will run, for example, 10. And then our update function is commonly one of those shorthand statements that we looked at earlier, like I++ or I-, if we were decrementing instead. You will sometimes see the third type with that plus equal or minus equal. So for example, if we started at 0 and went to 10, but we wanted it to increment by 2 each time, you would do something like this, I plus equal 2, and then we'd only get 5 iterations out of that loop because I is going to be 0, 2, 4, 6, and 8. So let's look at a for loop question. This is a different type of question that you might see on the exam. This requires a numerical response. It says, how many numbers will be printed by the following segment of code? So we have another segment that we need to trace through where a is being modified by our for loop, and we want to run it as long as a is less than 80. And inside the loop, we're going to print the value of a. And we want to know how many times do we print something? How many numbers are going to be printed by this? So similar to before, I'm going to keep track of the value for a and the output that we see, the results of any printf statements. Now the initialization statement for a for loop says that a should start at 1. So we'll give a an initial value of 1. And as long as a is less than 80, we'll continue to print values out. So 1 is less than 80. That's true. So we go inside the for loop, and we're going to print the value of a. And then we're going to update. We're going to say a should be equal to a times 2. So you might also see that written as a times equal to. And those are equivalent statements. Now 1 times 2 is 2, so A now has the value 2. We'll check our conditional expression. 2 is less than 80, so print 2. And then set A equal to A times 2. So we'll take this and multiply it by 2, which is 4. So 4 is less than 80, so print 4. And take A and multiply it by 2. So A becomes 8, which is less than 80, so we'll print 8. And multiply that by 2. So A now becomes 8 times 2, which is 16. 16 is less than 80, so we'll print 16 and multiply A by 2. So 16 times 2 is 32. 32 is less than 80, so print A. We'll print 32 and multiply A by 2. So A becomes 64. 64 is less than 80, so print A. And then multiply A by 2. So A will become 128. We check to see if A is less than 80. This is now no longer true, right? 128 is not less than 80. So we stop running this segment. We break out of the for loop. And now, how many numbers did we print? So we've printed 1, 2, 3, 4, 5, 6, 7 numbers. So 7 numbers were printed by this segment of code. Now let's look at a different type of question that might go along with loops. This one is similar to what you've seen in some of the quizzes, where there's an existing program, but we've taken some of the statements out of it, and we want to select from these drop-down boxes the correct expressions to go into the program in order to make it work. Now this program is intended to allow the user to enter a sequence of integers between -1000 and +1000. And they're going to be allowed to enter as many as they want, and they're going to end with -1001. So when we receive -1001, that's how we know that's the end of the sequence, that's the last number. And what we want to do is calculate the difference between the maximum and the minimum in the list and print out that value. So for example, if the user gives us a number sequence like this, and 95 is the first number, then -15, and so on, 99 is the last number, and then this is the indicator that they're done entering numbers. So in our list, 100 is the maximum, and 200 is the minimum, and the difference between those is 300. And we have this last little note that we are guaranteed they're going to enter at least one number that's not -1001. Okay. So then our program begins. We have the standard input-output library included. We have the beginning of the program. We have 3 integers, min, max, and value. Kind of note here the initial values for min and max. Min starts at 1001, where we know the biggest number the user is going to give us is 1000. This mechanism guarantees that any number they give us, since the highest valid number is 1000, is always going to be less than this. So when we're looking for the minimum, we know that any number they give us will be less than this initial value. Similar to max, any number they give us is guaranteed to be bigger than this number, except for their last value. Okay. The prompt is already written, says please enter your values ending with that sentinel value of -1001. That's followed by a scan format function, where we would like to read in the user's current value. So we need to select from these options something that has the correct syntax to read in the user's current value. Now the scan format function is here, and so are the parentheses and that semicolon at the end. So it's just what should be in between those parentheses. And we should have our control string with the percent code, the comma, then the ampersand, and the variable we're trying to read into. So we're trying to update value. Now we want to continue reading numbers until they give us our ending sentinel. So as long as the number they've given us is not the last number, then we want to do something with it. So as long as the value that the user's given us is not the final number, then we want to process that value. We want to check and see how it compares to min and max. So inside our while loop, we have a couple of if statements. This first one, we're missing the conditional expression for, so we're going to need some context clues from the rest of the program. If something is true, then we want to replace min with the current value. We want to assign value to min. We want to change min whenever the user gives us a new small value. So if the value they've given us is smaller than the current minimum, we'll update min with that value. Similarly, if they give us a value that's greater than the current maximum, then we want to update max, which is one of these statements. We want to update it with value. And the user will enter their next value, and we'll go back and check it again. Once we have all of their values, we should have the minimum for the sequence and the maximum. And we want to print out the difference between the two. So we want to print out the difference between max and min. Another thing that we talked about rather frequently is common errors associated with each of our modules. Syntax is very important. C only works correctly if you give it the correct syntax. So something you want to be on the lookout for throughout the exam is correct syntax, which might include missing or additional semicolons, semicolons where they're not supposed to be, or statements missing semicolons when they should have them. Incorrectly constructed conditional expressions. We did a video on common errors in if statements, and we did a video on common errors in loops, which commonly result in infinite loops. So you might see a question similar to this one. It says, to what should the conditional expression in the following if statement be changed? So it kind of gives you an indicator that this conditional expression is not quite right, and it needs to be modified in order to allow the program to work the way it was intended. In this case, it's looking for points in a certain range in order to print out this statement. This conditional expression that we see here is one of our common errors. We know that it will always evaluate to true, but the spirit of the expression is that we're looking for something between 12 and 25. So which of these potential choices gives us something between 12 and 25? Well, this first one says if 12 is less than points or points is less than 25. Now remember, the OR operator evaluates to true whenever either expression is true. So this expression that we've created here will always evaluate to true because points will always be either greater than 12 or less than 25. Instead, we want to use the AND operator to ensure that points is greater than 12 and points is less than 25. This third option is kind of similar, but it has a different range on it. It's not accounting for 12 and 25, it uses 11 and 26 instead. And this last option is just the negation of the original statement. So this one is the one that we are looking for. In a similar kind of style, this question asks, what's the problem with the following loop? It's a while loop that uses counter I, where I starts at 0. And as long as I is less than 100, we're going to print this statement. The problem with that is that I, since it's set to 0, will always be less than 100 because I is not updated anywhere in the loop. So this is an infinite loop. There's nothing wrong with the print format function. There's nothing wrong with setting I to 0 at the beginning, but it does run forever. So this is an infinite loop. Our last module before the exam was all about files, where we learned how to declare a file pointer, which uses the data type file in all capital letters, and asterisk to indicate a pointer, and typically either IFP for input files or OFP for output file pointer. We learned how to open a file using the fopen function, which returns a file pointer and takes as parameters 2 strings, the name of the file and the mode. There's only 2 modes that we talked about. We can have R for read or W for write. When we read from a file, we have to open it in read mode, and then we can use our file scan format function to read from the input file. This function has very similar syntax to our regular scan format function. So we typically place a single % code in our control string, the ampersand, and the variable that we're reading. The only new part is that it begins with F for file and has to include the file pointer that we're reading from as our first argument. Similarly, if we write to a file, we're going to call our fprintf function, tell it which file pointer we want to write to, print out our control string, and attach any arguments, any variables that we're trying to print out the value of. And when we're done interacting with a file, we will close the file at the end using fclose, which takes in a file pointer. So typically you'll call fclose on IFP or fclose on OFP. Now, IFP and OFP are just variable names, so you can, of course, call them whatever you want. IFP and OFP are stylistic standards, so you'll commonly see them called input file pointer or output file pointer. So this last question is another coding question. It says, write a segment of code that opens a file called numbers.txt for reading. This file is known to have 10 numbers in it. Read in each number and print an asterisk symbol to the screen if the number is even. If the number is odd, do nothing. And conclude by closing the file. So this is asking us for all of the file pieces. It doesn't ask us to declare a file pointer, so it would be fair to assume that this already exists. But for this example, I'm going to go ahead and declare num I and ifp. Now we want to open a file. We're given the name. Name is numbers.txt. And we're given the mode. We want to open it in read mode, so we'll use R for read. This file is known to have 10 numbers in it, so we'll set up a for loop that runs for 10 iterations. We want to read in each number. So we're going to read from a file with our fscanf, our file scan format function. From the input file, the number that we're interested in. It says if it's even, then we want to print a symbol to the screen. If it's odd, we don't have to do anything. We want to do that for each of the 10 numbers in the file. And when we are done, we want to close the file pointer. So this segment of code opens the file numbers.txt in read mode, reads all 10 numbers, and for each number checks to see if it's even. If it is, prints a symbol to the screen. If it's odd, it doesn't do anything, so we don't need an else statement. And when we've finished reading all of the numbers, we close the file. So that is a look at all of the topics we've covered so far this semester and some example questions to go along with those topics. I hope that you are feeling very well prepared, and good luck.